Hello and welcome to today's class. My name is Dr. Wanjala Titus. Today I'll be taking you through statistics and probability, and today we'll be able to look at the moment generating function of a binomial of a Poisson distribution. And today we'll be able to derive the moment generating function of a Poisson distribution. Thereafter, we shall be able to derive the mean and variance using the moment generating function. If you haven't subscribed into my channel, it's your time to subscribe into this channel for more information. Thank you. Let us start. We all know that the moment generating function of any distribution is always given as the expected value or the exponent tx. But now, under the Poisson distribution, the probability mass function is given by exponential negative lambda power x out of x factorial. Therefore, we all know that the expected value of x is always given as the summation of x heading to 0 all the way to infinity x f of x, which is the probability mass function for a discrete random variable. And therefore, since it's discrete, our x is going to be the moment generating function. Then we all know the probability mass function is given by this one. Let us now straight away derive the moment generating function, which is going to be the moment generating function is going to be the summation of x heading to 0 all the way to infinity exponential tx f of x, which is, or the probability mass function is this one, the exponent negative lambda is to power x out of x factorial. Are we getting it? Then what to do is we look at this one being our first constant. We have to limit it to the outside, the summation sign, which is going to be exponential negative lambda, the summation of x heading to 0 all the way to infinity. We have exponential tx lambda is to power x out of x factorial. Then what are we going to do? We can see an x here, an x here, so we have to summarize them or to combine them to be one, which is going to be the exponent negative lambda, the summation of lambda exponent t all by x. Are we getting it? Then out of x factorial. Stuck up. Thank you. Then what to do? Let a raised to power x be equals to lambda exponent t. It's because this equation is a little bit complicated. So as it will be exponent negative lambda, the summation of a raised to power x out of x factorial. In doing so, we can easily realize that this one is something that is well known, a common expression under the binomial theorem. Since this one is this way, under the binomial theorem, the summation of x heading to 0 all the way to infinity a raised to power x out of x factorial, always when under the binomial expression, it will give you exponential a. Are we getting it? All of this will give us exponential a. But what is exponential a? What is a? So our moment generating function will be a exponential negative lambda multiplied by exponential a. Are we getting it? Then in reaching there, exponential a is lambda exponential t. So it will be exponent negative lambda. We have exponent lambda exponent t. Yeah, that is it. So what to do? We are going to summarize the moment generating to be as the exponent lambda exponent t minus lambda. Are we seeing it? We are getting it clearly. Then, in conclusion, we will have the moment generating function to be exponent lambda into exponent t minus 1. So, our moment generating function will be the exponent lambda into exponent t minus 1. So that's how we derive the moment generating function of a binomial distribution, Poisson distribution. So in an exam, you'll be given a question to derive the moment generating function using the moment generating function of a Poisson distribution. For instance, you have been asked to derive the mean or the expected value of x. Since the expected value of x, we all know for a discrete random variable, we say it will be the summation of x, f of x, and this f of x is the probability mass function. But now the question is more specific to the moment generating function. It's asking you to derive the mean and variance using the moment generating function. So what we are going to do is we are going to find the mean from the first derivatives of the moment generating function with the t heading to 0. Are we seeing it? Then what do? Let us straight away differentiate this value of mean. And one secret here is, once you find such a thing to differentiate it, you will start by repeating the whole of this term, then differentiate the power. That's how we do it. For example, the derivatives of this one, the first derivative of the moment generating will be, you write what is there, the whole of it, into exponent t minus 1. Then you differentiate what is the power. You differentiate the power only now. So the power will be lambda into exponent t minus 1. Then all of these with the t heading to 0. Are we getting it now? Now, let us come and conclude. This one will be exponent lambda into exponent t minus 1. We will multiply by, when we differentiate this one will remain as a constant. It will be lambda exponent t. When you differentiate this one, it's just exponent t. But when you differentiate this one, it will be 0. So it's over. So we say with all of these heading to 0. So in reaching there, our expected value of x is gonna be, we replace the values of 0 here. But let us at least summarize this one. We say when we combine the two terms or when we multiply, it's going to be lambda exponent lambda into exponent t minus 1 plus t. I think from the laws of indices. Then what do? We replace from this equation with the t heading to 0. So it's going to be lambda exponent lambda into exponent raised to 0. Any number raised to 0 is 1. So it will be 1 minus 1 plus 0. So this one will give us 0. Multiplied by this one is 0. So the answer is going to be lambda exponent 0. Since it's lambda exponent 0, then the expected value of x will be lambda. That is how we derive the mean from the moment generating function. Let us now define variance. B, you have been asked to define the variance. And we all know variance is always given by the expected value of x squared minus the expected value of x, but this one is squared. This mean, this one is mean. So from this one, we say the expected value of x squared, it will be the second derivatives of the moment generating function with t heading to 0. Then from there, we will be able to replace from the mean. So in this, from this equation, let us find this one. Then this one already we have it from the mean. So we'll square the mean, but this one we differentiate the second derivatives. So the second derivative of the mean is going to be, we are going to differentiate exponent. It was lambda exponent into lambda into exponent t minus 1 plus t. That was our first derivatives. But we said in differentiating such equations, we start by writing the whole of the equation, then we differentiate what is the power. Then we say it will be lambda exponent lambda into exponent t minus 1 plus t. Then we differentiate now what is in the power, which is going to be lambda into exponent t minus 1 plus t. The whole of this with the t heading to 0. Are we there? Then what do we do? What we are going to do is now to differentiate this one, we multiply by this one. So it will be lambda exponent lambda into exponent t minus 1 plus t. When we differentiate this one, it will be this one, all obvious, it will be a constant. Then when we multiply by we differentiate this one, it will just remain exponent t. Then this one will be 0, this one will be 0, so no need, it's over. Then with respect to t heading to 0. Then what are we going to do? Let us combine the two. Or let's not start by combining. Let us replace the value of 0 first. Then this one is going to be lambda into exponent lambda into exponent t, which is 0. This one will be 1 minus 1 plus 0. Are we there? Then it will be lambda exponent 0, which is just 1. So this one will be lambda exponent 0 multiplied by lambda exponent 0. But this one is 1. Exponent, any number raised to 0 is just 1. So our expected value of x squared will be lambda times lambda, which is equals to lambda squared. But variance is always given as the expected value of x squared minus the expected value of x but squared. Are we there? But always this one, when we expand this one, is going to be the expected value of x into, it will be x into x into x minus 1 plus the expected value of x. So variance will be the expected value of x into x minus 1 plus expected value of x minus the expected value of x squared. This one now. This one is this one. Then this one, we replace it from there. So it will be, if this one has given us lambda squared, so we'll have lambda squared plus this one, which is the mean, which is lambda, then minus lambda, which is the mean again, but we square it. So this one will cancel out this one. So our variance will be lambda. So that's how we derive the mean and variance from the moment generating function over Poisson distribution. Thank you for watching. Remember to subscribe, to share, and like and comment from the video above. Thank you and bye-bye.